Hi everyone, let's work through this polynomial, graphing it using our curve sketching steps. All right, first things first. The domain of a polynomial is all real numbers. Next, let's find the x and y intercepts. The x-intercept is the x value when y is 0, and the y-intercept is the y value when x is 0. With the x-intercept setting y equal to 0, this is not an equation that I can easily solve, so I'm going to skip this for now. One of the beauties of the curve sketching steps is that there are so many that sometimes we can skip one and still figure things out. The y-intercept is pretty easy because this is just replacing x with 0. So this is 6, so we have the point 0, 6. Let's go ahead and graph that. All right, so we skipped the x-intercept, and we're going with the y-intercept right there. And now determine the behavior for large absolute values of x. This is the end behavior. And for this one, we talked about limits and such at the beginning of the semester, but I think it's easier just to use our algebra rules of thumb. So with the algebra rules of thumb, we're going to look at the leading term, the term with the highest exponent. So here 4 is the highest exponent. So we're going to say for large values of x, this behaves like y equals x to the 4th, where that term dominates. And what I know about this is that if I plug a really large positive number in for x, my output is a really large positive number. So I know that as x gets large, y gets large in the positive direction. And if I plug in a large and absolute value negative number, so like negative 1,000,000, negative 1,000,000,000 in here to the 4th power, it's going to become positive. So we're going to be going up in both directions because the y output will always be positive, and as x gets really large, y is going to get really large as well. So we know here that we're heading up and up in some way. Horizontal and vertical asymptotes, those were typically going to come from our rational functions, so we're not going to have asymptotes here for our polynomial. Intervals where f is increasing and decreasing. All of these next ones here, 5 through 8, are related to the derivative, so we'll go ahead and take the derivatives and look at sign tests here. So we know we're increasing when the first derivative is positive, and we know we're decreasing when the first derivative is negative. So let's go ahead and take the derivative here. Just our power rule, 4x cubed minus 6x squared. And we're going to be interested in the critical numbers. The critical numbers are when the derivative equals 0 or when the derivative does not exist. Polynomials exist everywhere, so we don't have to worry about that does not exist. So now we're going to set our derivative equal to 0. And looks like I can factor out a 2 since both of the coefficients are even, and an x squared right there, which is going to leave me with 2x minus 3. If the product of two factors is 0, then either the first factor is 0 or the second factor is 0. We can solve here to get our critical numbers, so 0 and 3/2. We're going to do a sign test here. So we'll just put these down in order. The spacing doesn't matter too terribly much here. This is 0, and this is 3/2. These are where our derivative is 0. So we're looking here for the sign of the derivative. And the way I'm going to do this is I'm going to pick a test point that falls on either side of my critical numbers here. So I could test, for example, x equals -1, test x equals 1, and let's test x equals 2. Any value to the right here would have worked, any value between, but I try to pick pretty straightforward ones that are easy to calculate. So I'm plugging these not into f, but into f prime, because that tells me something about what the function itself is doing. So f prime of -1. Now here I don't actually have to evaluate this. I can just look when I plug -1 in right here. -1 squared is going to be positive. -1, here I'm going to get a -2 minus 3. That's a negative result. Negative times positive is negative. So I know everything to the left of 0 is going to have a negative derivative, so decreasing. Then I'm going to test in the first derivative 1. 1 squared is positive. 1 substituted for x here, 2 minus 3 is a -1. I want to point out here that just because we have a critical number doesn't mean we always change the sign of the derivative. This isn't a mistake. This is just the way this function works. Now we're going to sub in 2. Again, 2 squared is positive. And then here, 2 times 2 is 4, minus 3 is 1. That's going to be positive. So positive times a positive gives me a positive right here. What does this tell me? This tells me, this is the sign of f, this tells me that f is whoopsie, that f is decreasing, because the derivative is negative, that's the slope of the tangent line. Here f is decreasing, and here f is increasing. Now when we go from decreasing to increasing, that tells us that we're going to have a relative min when x equals 3/2. So let's go ahead and calculate, since we're going to be plotting, what that looks like. So to figure out the value of the relative min, we're not going to sub into f prime. That'll give us 0. That's where we have a turning point. We're going to sub it into f. So f of 3/2. Let's see what we got here. What was f? This is, oh goodness, this is 3/2 to the 4th minus 2 times 3/2 cubed plus 6. All right, 3 to the 4th, let's see. 3 times 3 is 9, times 3 is 27, times 3 is 81. 2 to the 4th, 2, 4, 8, 16. Minus, let's see, we'll have 2, 4, 8 on the bottom here. 3, 9, 27, 54 on top. And then plus 6. This is kind of a mess, isn't it? All right, well, let's keep working with this. This is 81 over 16. We're going to double these, 108 over 16. And let's just leave this as 6 for now. So let's see, 108 minus 81. Our negative was bigger, so negative 27 over 16 plus 6. Here I'm just going to go with mixed numbers. This is -1 and, 11/16 plus 6. So 6 minus 1 is 5. 5 minus 11/16 is going to be 4 and 5/16. So we have the point 3/2, 4 and 5/16. 3/2. Here's our 3/2, and here's our 4. 5/16 is going to be close to a 1/4. So that was going to be a relative min. Right there. So let's go ahead here as well, so we can work on filling in our shape. Look at our derivative, and we were interested at 0. We had a negative sign up to 3/2 negative, and then we switched positive. So we know that our function is generally coming down to this point and then generally heading up, but we're going to have to look at concavity next to see exactly what happens. We also know that the slope of the tangent line was 0 here, so our curve is going to be flatter right here. If the tangent line has a slope of 0, that's going to look fairly horizontal. So let's come on to our second derivative. So this was our relative min at x equals 3/2 and 4 5/16. And now let's come to our second derivative. So let's see. We know that we have f is concave up when the second derivative is positive, and f is concave down when the second derivative is negative. And so we need to take the second derivative. So I'm looking up here at my first derivative. So this is going to be 12x squared. And this is going to be 12x. Nice 12s there. So again, I'm looking for where I want to know where the second derivative is 0 or where it does not exist, because that's where I might change signs in my concavity. It's a polynomial, so we don't have to worry about the does not exist. So let's make this 0. I'll factor out a 12x. I'll be left with x minus 1. Again, the product of two factors is 0, then either 12x is 0 or x minus 1 is 0. So we're looking at x equals 0 and x equals 1 as our points of interest here. So now when we do our sign chart, again, we're looking now at the second derivative, and we're going to look at 0 and 1. And we're going to test some points in between there. This is where the second derivative is 0. So let's test x equals -1, x equals 1/2, and x equals 2. Anything in those intervals would work. What are we subbing into? We're subbing into the second derivative. So this is going to be -12, and this is going to be -1 minus 1. That's going to be a negative value. So negative times negative, this will give me positive. Look at the second derivative, 1/2. This will be positive. This will be 6. 1/2 minus 1 is negative. Positive times negative, this will be negative here. And then finally, we'll look at 2, positive and positive. So that means we have an inflection point when x equals 1, and we have an inflection point when x equals 0. And what's going on with f here? Well, f is going to be concave up, f is going to be concave down, and f is going to be concave up. So let's look at where our inflection points are. Again, we're not subbing into the second derivative here because that'll give us 0. That's where we're changing. We're subbing back into our original function. So to get the inflection points, we need to look at f of 0, which we've already figured out above is 6, and we need to look at f of 1. Oh, 1 is much better to sub in here than what we had with the 3/2. So I forgot what f was already here. What was f? X to the 4th minus 2x cubed plus 6. X to the 4th minus 2x cubed plus 6. So subbing in 1 for x, we get 1 minus 2 plus 6. And it looks like that's going to be 5. So we have inflection points at 0, 6, and 1, 5. 0, 6, this is an inflection point, and 1, 5. That's an inflection point as well. And we can come in here and we'll put this all together. This is going to be our second derivative. And now we were interested, this was 0 and 3/2, 0 and 1. And let's see, I think we were positive, negative, positive. I forget. Let's go back and look. Positive, negative, positive. Yep. All right, so we have these regions that are going to be similar. So I'm going to draw a line here because we've got interesting things happening at 0. We've got interesting things happening at 1. So I'll line that up. We've got interesting things happening at 1.5. That's where we have changes going on. So what's going on here? Well, looking here, we're decreasing. That means we're decreasing, going like that, and we're concave up. So this part of our graph is going to look like that. So we're coming up like that. Then here we have a negative, so we're decreasing still, and now we're concave down. Oops, kind of missed it there. Let's try that again. And notice that here we look like we could have a flat tangent line, right? A horizontal tangent line, and we had a 0 slope there, so that's good. Then we come down to this next region here. We're decreasing and concave up. Decreasing looks like this. Concave up looks like this. So we're coming like that. And then now we're going to be finally increasing and concave up. So we're coming up like that. Let's erase these guides here. They match what we have. And that in general is what our graph looks like. Let's go ahead and label some points here. We had 1, 5. We had 0, 6. This was our relative min. This is an inflection point. This is an inflection point, change in concavity. We're decreasing all the way to 3/2, and then we're increasing. So we can always check that. Let's see, x to the 4th minus 2x cubed plus 6. X to the 4th minus 2x cubed plus 6, and yeah, that looks like our graph. So if we look at our points, we have the 0, 6 right there. This was 1.5, 4 point something, and then we can see our inflection point 1, 5 seems reasonable right there. So that's a problem in total. Let's go back and make sure that we hit all of our steps here. So we got the increasing, decreasing, relative extrema, concavity, inflection points. And in this case, I don't think it was really necessary to add more points, although you can always do so.